Make sure it's recording.
There it is.
F. And so in both directions, he yes, are we, we're on. Okay, all right, thanks. So a split group is, it's Chevrolet's construction automatically hands you the notion of a dual group over the same field, but he didn't, I don't believe he made terribly much of it. But Langlands, again, I think not with, I guess he was referred to Chevrolet's article. In any case, a split group is a group whose maximal torus, which has a maximal torus that's defined over the ground field. The dual group is the split group whose maximal torus is the dual maximal torus. And there's a general construction of a dual torus attached to any torus. So in any case, for GLN, Chevrolet was actually talking about semi-simple groups, or I guess simple groups, but GLN is a reductive group. But nonetheless, the dual group construction introduced by Langlands gave dual group for GLN, the group GLNC. And as I mentioned before, if the group happens to be, for example, symplectic group, then the dual group is sp2n, and the dual group is so2n plus 1, taken over the complex numbers, and so on. But what's really striking is that, and this is just the beginning of Langland's article, attached to an automorphic representation, an object which seems quite abstract and maybe not all that promising. I think that's the way people saw it when they first saw Langland's article. I don't know whether they thought that, but attached to that are some very concrete data, a family of conjugacy classes in the dual, complex dual group. So in particular, if G equals the general linear group, GLN, then C pi P is the conjugacy class, a semi-simple conjugacy class in GLNC. So this is a set, these are complex numbers, and they're to be taken up to permutation. And last time, and I think even the time before, I described, I think in a rather clumsy fashion, the way that you get these data appear in the construction of unramified representations, which are the constituents at almost all places of an automorphic representation. So they're the induction data that give you the local constituents almost everywhere. They are also eigenvalues of a family of operators, the Hecke algebra, which act on L2 of GA over GQ. So they have two different and equivalent ways in which they arise. But the point really is that they're very concrete. These are very concrete objects. And I have a bunch of notes and comments that I was supposed to make at various stages. This looks like a lot less data than would characterize the automorphic representation. This looks like it includes a lot more than these things. These things look possibly at first glance like they're sort of side issues. They're not. They're absolutely at the center of automorphic representations. And in many cases, notably for the case of general linear group, and if G is a general linear group and pi is occurs in the discrete spectrum of L2 of the general linear group modulo the center and modulo GLNA modulo the center and modulo GQ, then these actually completely determine pi. I guess that's called the theorem of strong multiplicity 1. In any case, these are at the heart of automorphic representations, and they're, at least at first go around, they are the objects which I would say characterize the fundamental aspects of the Langlands program. Now, in particular, part one, I guess, was the notion of an automorphic representation. So part two of this sort of little discussion is the notion of an automorphic L function. So if you have a split group and you have an automorphic representation, then you've got a family of conjugacy classes in the dual group. Now, if you're in the case of GLN, the dual group is just GLN, and you really want a set of conjugacy classes in a general linear group to be able to mimic the definition that we had for an Artin L function, namely as basically a product, an Euler product built out of characteristic polynomials of these things. That's not what you have for a general split group. The dual group is something different from GLN. So you need an extra piece of data. And again, this must have caught people by surprise in Langlands' article, and they perhaps scratched their heads, didn't know quite what to make of it. So automorphic L functions depend on automorphic representations pi of GA, but they require an extra piece of data and a finite dimensional representation, not a representation that's unitary. Those would usually be infinite dimensional, but a finite dimensional representation R of the dual group. G goes to GL and C. So for some general linear group, and which is the image of a finite dimensional representation. And with that understanding, we define, or Langlands defined, the automorphic L function, whose local constituent at P of S, so it's going to depend on pi, and it will also depend on the finite dimensional representation R, and it is simply defined exactly the way it was defined for an Artin L function, namely the inverse of the characteristic polynomial of what you can construct from these objects, but evaluated at p to the minus s. So specifically, it's the determinant of 1 minus r. Okay, so I've got CP pi, a conjugacy class in the dual group. This is a representation of the dual group. So this then is conjugacy, can be mapped to a unique canonically to a conjugacy class in GLNC. And so here you have a conjugacy class in the general linear group. This is basically the characteristic polynomial, which is we would take rather than x, we take it at p to the minus s, and we take the inverse of that characteristic polynomial. So this is the characteristic, essentially the characteristic polynomial of this conjugacy class, the semi-simple conjugacy class in GLN. So that's the local constituent. And then we would define the global L function, and we're missing a little bit of data. This would be the global L function in which we throw away a finite set of primes, including the Archimedean primes, but capital S, I, R, is the product by definition, be not in S. So almost all primes, the primes which give unramified conjugacy classes of LP, S, I, and R. And so this converges, depending on pi, certainly converges if the real part of S is sufficiently large. So this is a Dirichlet series, like the Artin L functions. It's a Dirichlet series. With Euler product. Okay, and this, I think, if I'm remembering correctly, this was the first of Langlands' 7 questions, to which Langlands, for which Langlands conjectured. I guess I do it like this. So conjecture that is still far from known. That LS, little s, I, R, has analytic continuation. And functional equation. And a functional equation that relates. So Langlands did it much more completely than what I'm doing here. Right at the beginning of his, I think, of his first of 7 questions, he introduced this, not only this, but he introduced further factors at the finitely many places that are missing, including the Archimedean places, which would then lead to a much simpler and more elegant functional equation. I'm leaving these out for the moment, but nonetheless, the functional equation relates in a concrete way its values. Well, it's relating the values L upper S of little s pi r and L upper S of little s pi, and actually the contragradient representation R is a representation of the complex dual group R check of X equals R of X transpose inverse. Oh, I'm sorry, did I? No, sorry. It relates its values at S and 1 minus S, with the understanding that you have to often take the contragradient representation here. And the actual functional equation, if you wrote it for this, would be a little bit complicated, but Langlands pointed out that you could also, conjecturally at least, define local L factors at all places S, including Archimedean places, where they take the form of basically gamma functions. And he then conjectured that there was a functional equation that related these things. Yes, 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 please. So if pi is a cuspidal automorphic representation, then it converges, I guess, for real part of S greater than 1. So for GLN, I guess, at least, this converges. I think you're fine. It's conjecturally it converges, conjectured to converge for real part of S greater than 1, but that requires a conjecture that is not as deep as this conjecture, namely it requires Ramanujan's conjecture for the...
No, classically, if you use the GL2, you easily get convergence in a half because you can put some dot. Not Ramanujan, but
oh, you mean in a half plane?
A half plane, which is what that's all exactly here. It converges in some half plane.
The fact that the representation pi is unitary gives you convergence in some half plane. Unitary is a condition, a fairly strong condition on the representation pi, and it gives you convergence in a half plane. I think I'm right on that. But you expect, if pi is a cuspidal automorphic representation, that you get absolute convergence in the plane real part of S bigger than 1. If it's just something that occurs in the discrete spectrum, you get convergence in another, conjecturally, you get convergence in another half plane that's a little bit to the right of that, because there are things that are not cuspidal that will occur in the discrete spectrum, like the trivial one-dimensional representation, for example. But we're okay just assuming that it converges in some right half plane. I think that's probably the way Langlands phrased it. So what did I have remarks I wanted to make on this? No, I've already said that. The theorem that for GLN that says that these data, these families of conjugacy classes completely determine the automorphic representation pi if it lies in the discrete spectrum, or at least certainly if it's a cuspidal automorphic representation, that is known as the strong multiplicity 1 theorem for GLN. Okay. Well, that sets the stage for Langlands' well, maybe for example, let's call this example 1, and it's an example pertaining to L functions. If G is equal to GL1, and then what happens if I is the standard representation of the dual group, GLNC, which in this case is GL1C, and so this is just the standard one-dimensional representation of that. So this is the standard one-dimensional representation of G hat. equals G equals C star. Then analytic continuation. And functional equation. Is classical. It was proved by Hecke, and in many cases, and Tate, I guess, in all cases. Tate, and it was Tate's thesis, basically, and actually he was working over a more general situation, over a ground field that's any number field. But in this case, an analytic continuation and functional equation was well known. Langlands, I think, had an inkling, and maybe he even had a pretty good idea of how it would go. In a more general example, he certainly makes remarks in his paper to this effect. The case that G is equal to GLN, and R is again the standard representation of GLN. So this is the standard n-dimensional representation of G hat, which is GLNC in this case. So it's now known that analytic continuation and functional equation holds in this case as well. Analytic continuation and functional equation of LS, and in a better form where the local constituents are also put into this at the bad primes S, but in particular analytic continuation and functional equation for LS pi R, so R being the standard representation, and that's usually just written as LS pi because the data already sit in GLNC. And this was proved by Godemont. I guess Langlands was in pretty regular communication with Godemont and his student, Jacquet. But this was proved, it was, I think, published, I think it was 1970 in a Springer lecture note series. And so that was available. Langlands assumed that it was available or close to being available. But I've said that analytic continuation and functional equation is far from proved for one of these more general things. And what's the problem? What's holding us back if we already know it for these are called standard L functions. These are called standard automorphic L functions. What's holding things back? Well, what's holding back is the big one. The principle, so if 2 is automorphic L functions, the big one, which was not named at the time, it was stated probably rather in a less appealing way. I don't know who coined the notion of functoriality. It probably came maybe 5 years after Langlands' article. Perhaps Burrell coined it. But in any case, what's the heart of all of this is the principle of functoriality. And so this is a conjecture that Langlands stated without using this word, and he stated it in really more complete form to include both local and global assertions. But I think at first go around, what is really the concrete and most striking thing these days about the Langlands program is the existence of these data, this family of semi-simple conjugacy classes in the dual group for almost all prime numbers, something that's very concrete. Okay, in any case, this is a conjecture in Langlands' original article. And perhaps because he also put in more general, did it more generally by putting in the constituents of an automorphic L function or automorphic representation at the ramified places, but it didn't perhaps get as much publicity and didn't look as concrete as it would look just for this family of conjugacy classes. It can be stated as follows. Suppose that, so we've got a split group, G over Q. Suppose G prime is another split group. Over Q. And suppose that we've already got G, a split group over Q, and that rho prime is, so for each of these groups, we've got their dual groups, so G prime hat, and we've got the dual group of G, and so suppose this is a complex analytic homomorphism from one to the other. So, so this is a homomorphism. And suppose that for this assertion of this, we take an automorphic representation, not of G, but of G prime. So pi prime is an automorphic representation of G prime. Well, functoriality is the innocent little assertion that there's an automorphic representation pi of G. This is the conjecture. Pi of G such that the data, this concrete data of conjugacy classes for G prime, maps to that concrete data for G by rho, the given homomorphism. That's a simple enough thing to do. These are complex algebraic groups. You can certainly talk about homomorphism. This is a general linear group. You can just talk about an n-dimensional representation of the dual group. Very innocent looking data, and innocent looking data that come from pi and pi prime. Assertion is there's an automorphic representation pi of G such that CP pi, the data attached to P for almost all P and pi, such that this is the image, rho prime of CP pi prime. And this would be for every P just outside. We aren't caring about how big that finite set is. It would have to match both the finite set attached to pi prime for G prime and pi for G, but for every P outside a finite set, this, and so this is understood to be the conjugacy class. Rho prime maps a conjugacy class in the smaller group, then its image in the bigger group will generate also a conjugacy class in G hat. This, by definition, is a conjugacy class in G hat. The assertion is that they are the same. Well, now, if we're used to Art and L functions, well, let me just say then what this would say for L functions before I go on. So, in particular, if R, in particular, for every representation R, of G hat into GLNC, we would have L of S, pi, and R being equal to L S pi prime, but the representation rho prime maps the dual group of G prime to the dual group of G. R is a representation of the dual group of G, so this would be the composition of R rho prime. That's just a restatement of this identity. So this is, if we're dealing with I'm giving it away a little bit to what's going to the relationship that is going to come between automorphic representations and automorphic L functions and Art and L functions. You're going to have to take a slightly more general situation to encompass that. But the analog of this statement or this statement for Art and L functions, or for the data that goes into Art and L functions, is trivial. It just follows. It's trivial. So I speculate it's not trivial at all, not at all for automorphic representations, even though the relation between data attached to automorphic representations and the data attached to Art and representations of the Galois group that give Art and L functions, even though that data, those, as we'll see presently, the data, one set of data is included in the other. But for people that were used to Art and L functions, I speculate that they might have thought, if they got to this, they said, well, come on, how difficult can that be? This is trivial in the case if you're dealing with data that comes from Art and L representations of Galois groups and Art and L functions. But it is not trivial by any means. This is still, it's been done, and this has been proved in a significant number of cases, I think it's fair to say. But the cases where it remains to be proved dwarfs the cases where it has been proved. I think it's fair to say it's far from being proved. Okay, so to see, well, let's just do a couple more. Let's see an example of how this would work. Any questions, Kumar? No. I hope I'm not. I mean, this is pretty elementary for people who are familiar with this, but I still get excited knowing knowing of these things. This data that's here. Okay, so example. So why don't I call this 1? I had example 1 for L, which we had to apply to L function. So let's call this example 1, because it's an example that applies to functoriality. So let's take G prime to be arbitrary. And let's take G to be GLN. And R, let's take rho to be, I think we're calling it rho. Rho prime equals, well, I'll call it, let's take rho equal rho. We'll just take R to be, rho prime to be equal to R. Just a representation of GLN. No, I'm sorry, I don't think I want that. G prime is arbitrary. G equals GLN. And let me take R. So now I'm interested in an automorphic L function. So R is the standard representation. So rho prime. So G is arbitrary. G is a general linear. Rho is a map from G hat prime to G hat. And I want to take that to be GLN C. In other words, I want G equals GLN. So I want to consider the assertion of functoriality, where you have two different groups, G prime and G, and a homomorphism from the dual group of the first one to the dual group of the second one. I want to take, yes, I'm sorry. Yes, GL. G is equal to GLN. So I want to take G to be GLN. Its dual group is GLNC. And so functoriality says you've got to have a map from the dual group of G prime to the dual group of G, which is GLN in this case. What does it say? Well, let's look at the L functions, and where we would take R in general is a map from the dual group of the second group G into GLN. Well, I'll take R to be the standard representation of G hat. Okay, so this would be the standard representation that simply embeds G hat into itself. And let's then look at the L functions. So we've got, where are our L functions? We've got them here. Question? Question? No, no, no question. Stop me, please, if anybody. So, then the left-hand side, so what do we get for these L functions? Then the left-hand side of star, what do we get for that? Wow, this is just, this equals, I is an automorphic representation. So we've got pi prime, and we've got, so assume functoriality.
To be consistent with your notation from before, you want rho prime or rho?
Thanks, yes, rho prime, thanks. I want rho prime going from G prime to G. to GLN. So rho prime, and I want rho prime goes from G to G hat, and then I want R from G hat to itself. In other words, R to be the standard representation. Yes. So then assume functoriality. Okay, and so then on the right hand, so i.e. pi prime then goes to pi. A pi prime gives you an automorphic representation of pi once you've fixed rho prime. And so the left-hand side of star R is the standard representation. This is just what we're calling the standard L function. L of S pi, standard L function. Okay, so that has analytic continuation and functional equation by Jacquet-Gaudemont. Has analytic continuation and functional equation by Jacquet-Gaudemont. That's what we got over here. But this thing, the notation's different. What I had earlier when I was defining an L function for a general group was this pi prime was G prime. Pi prime was G. So, but this is, if I think of G prime instead of G here, this is a general group G prime, a general automorphic representation pi of G prime A, and a general the right-hand side of star, because R is the standard representation, just equals L S pi prime rho prime. So the notation's different. What we had before for a general L function was this was attached to G, and rho prime was a representation R of G hat. Here, pi prime is associated with G prime, and rho is a general representation of G prime hat. But this equals this, and this is therefore, even though the notation is different, has to be different in this to incorporate functoriality, but this is a general automorphic L function. That's the right-hand side. The left-hand side is a standard automorphic L function for which we know analytic continuation and functional equation. The right-hand side is a general automorphic L function. So functoriality implies functional equation and analytic continuation. Okay, so next time we will go slightly more general. We'll deal with quasi-split groups. All of the stuff goes over for quasi-split groups in a way that doesn't really even need too many new definitions, but it has, that's already a stunning consequence. And when we look at what happens for quasi-split groups, this has to be put in a slightly more general setting, and then the rest of the stunning consequences of the Langlands program are then come through in that. I think that's the way it works. And any comment or?
He requires this. You have to be like a holomorphic mapping set, right?
I have, yes, when I talk about a map, it's understood to be satisfy all the right properties. So if it's a map between complex dual groups, you require it to be holomorphic representation or algebraic representation.
Because on the dual group, there are complex points, and so you can ask for holomorphicity, right? Over there as well, when you say a finite dimensional representation R, is that an algebraic representation?
Yes, that's right. Any representation between dual groups or complex groups, I guess, is we would understand it to be analytic. Right. Yes. Yes. So long as it's yeah. Yes. Yeah. Yeah. Questions? Questions? Well, I think you probably know this stuff. You know this stuff pretty well, but
love to hear it.
It's nice to hear. Yeah.